Okay, we're talking about information theory. Two aspects of information theory we're going to cover in this course. They are basically data source coding.
Professor,
Yes?
about the quizzes, are we going to have a sixth quiz?
Yes, that'll be next week. Source coding. By which I mean compression. And channel coding, by which I mean error detection and correction. So, last time we were talking a little bit about compression, and we said there's this fundamental quantity called the information theoretic entropy. So let's let x be a random variable. Where x takes values in some set, let's call it script x, like that, and each of those events has a probability. So let's make x a discrete set. It is possible to extend entropy to talk about continuous random variables, but let's not worry about that. And in this course, we'll just assume that everything is discrete. Okay, so let x be a random variable, and x takes values in this set, script x. Then the entropy h of x is equal to the sum over all elements of the set, or all values of the probability of that outcome times log 2 of 1 over probability of x. And thanks to a property of log, I don't have to take that ratio. I can just write this as minus the sum of probability x log 2 probability of x. And thanks to Claude Shannon, the founder of information theory, we know the following. So Shannon's source coding theorem so any source with letters in x of length n, so in other words, I have a length n of letters from x. So in other words, this is just a vector of length n that contains elements of x. Can be represented with n h of x bits, and so this is there's two sides of this theorem. Any source with letters in x of length n can be represented with n h of x bits. So there do exist codes to compress an n-fold vector of x into n h of x bits, and no more compact representations exist. No more compact, let me put in, lossless representations exist. So in other words, if I have n, so for example, my example last time was marks. So I said the set of possible letters was A, B, C, D. So in other words, if I'm going to represent the marks generated by people in this class, then what I have is I think there are 13 students in this class. So we have, there are 4 elements of X. So N is 13. So we start with a vector of marks with length 13. And we calculated last time, so using a contrived distribution, he said, okay, probability of A is a half, probability of B is a quarter, probability of C is an eighth, and probability of D is an eighth. So what we said was, or excuse me, what I can calculate entropy to be is the sum over X in set script X. Probability of X, log 2 probability of X, minus, which is equal to 1/2 log minus 1/2 log 2 1/2 minus 1/4 log 2 1/4 minus 1/8 log 2 1/8 minus 1/8 1/8, and we established last time this is equal to 1 3/4. Or I can write that as 7 over 4. So the most compact possible representation of this source is for each letter in my vector, I can replace it with, on average, 7 over 4 bits. So the most compact possible representation of the marks in this class would have length 13 times 7 over 4, which is 91 over 4, which is 25.25 bits, I think. No, that's wrong. 22 3/4 bits. In principle, it should be possible to represent the marks in this class with 22 3/4 bits. These arguments, Shannon's source coding theorem holds as, actually, more formally, it holds as n goes to infinity. For short n, it doesn't necessarily hold. But the idea is that h of x gives you the rate of compression for any sufficiently long file. So for instance, if I had 1,000,000 marks, that's sufficiently large that this argument holds. For 1,000,000 marks, I should be able to fit that in 1,750,000 bits. Whereas naively we argued that each of these can be represented with 2 bits. So I can just say this is 00, 01, 10, 11. The length of that would be 2 million bits. So clearly there's a saving of 250,000 bits in the compression.